Welcome to CMOS RF integrated circuits. This is we are still in the third module, that is we are talking about passive components, and today's lecture we are going to talk about inductors. Before that, I am going to briefly recapitulate what we studied in the previous lecture on capacitors and resistors. So, resistors were easy. Resistors were easy, units are in ohms per square, typically that is what the foundry is going to give you. You basically count the number of squares and that gives you the resistance of the entire track. Fine. Capacitors, whenever you see two parallel plates, it forms a capacitor. Now, neat ways, you have to remember that the field between the two parallel plates, if the plates are infinitely large, the field is perfectly vertical. If the plates are limited in size, which is the case, then there is going to be fringing along the borders. So, the capacitance, net capacitance is going to be proportional to the area. So, there is going to be A epsilon by D, that component is going to be there, and in addition there is going to be a little bit because of the perimeter, that is going to be proportional to the perimeter. Fine. On an IC, how do I make a capacitor? I can take two metal layers and build a capacitor between them. That is one way of doing things, but the distance, the separation between these two metal layers are quite significant, which means that I do not get very good capacitance density. I usually burn up a lot of area to make a small capacitor. Then I can use the MOSFET itself to make a capacitor. The gate to channel, the separation between gate to channel is well controlled and it is quite small. So, I get good capacitance density, but this comes with caveats. The caveats are that I get very large parasitics to ground and I also end up with a capacitor that is required to be biased. So, the DC voltage between the gate and the channel has to be more than a threshold voltage to make this work. All right. Next idea was to use two wires, two tracks, and the separation between the two tracks can be made very small, that is the size of the resolution of the technology. If you are in a 0.1 micron technology, then that could be as small as 0.1. The thickness between the gap between two layers is much larger than 0.1 micron in a 0.1 micron technology. So, anyway, so I can use that thought, that idea, and I can make a wire to wire kind of capacitance in a sense. There also I will be getting some parasitics, but if I choose a high enough metal layer, then the parasitics are less. I can basically make something which is fingered the way I have drawn it. I do not know if the 3D picture was comprehensible, but this is more or less what I wanted to show. So, top layer has fingers. So, there are two sets of fingers, and between every two fingers there is going to be a side to side capacitance. Now, just like I have got 4 hands like this, 2 hands like this, I could put 2 more hands below this in the opposite configuration, and that would give me the vertical capacitance as well. That is what I was trying to show in this diagram over here, this 3D picture. I do not know if it was very clear or not, but anyway. So, this is what I wanted to show in this picture. All right. So, now there is one more thing, one more small thing that you could do. Okay, basically the side view, the cross sectional view is given here. Okay. Now, making these connections, all the 2's need to be shorted together, all the 1's need to be shorted together. How do you achieve this? So, the layout style is something like this. On metal 1 layer or metal X layer, I put horizontal strips and on metal X plus 1 I put vertical strips. Okay. And I want this wire to be 1, this is 1, this is 1, I want this to be 2, this to be 2 and this to be 2. And similarly, I want this to be 1, this to be 1, this to be 1 and this to be 2, 2 and 2. So, I need to make a short between all the 2's. So, I am going to put a set of vias over here and over here. I am going to put a set of vias here, here and here, set of vias here, here and here. And then again I am going to put, I need to short all the 1's. So, I am going to put so, vias are the connections between the 2 metal layers, right. So, this could be my layout. So, now everything is connected, now I get what I wanted. So, I get the side to side capacitance as well as the plate to plate capacitance. Now, of course, my drawing is not particularly nice. What you have to make sure is that this width is large and the gap between the 2 is small. So, you have to make this width large and the gap small. Okay. So, as long as you do that, you will get a very high capacitance density. Okay. You are basically taking advantage of both metal to metal capacitance as well as side walls, right. So, these are basically how we build capacitors on an IC. There are a lot of other interesting ways you can make fractals, etc., and try to compress an infinitely long line segment in a finite amount of area. You can do stuff like that, and anyway. So, there are a lot of other ways of making very good capacitors as well. Just keep that in mind. Okay. Now, we move on to the next item on our list of passives, and we are now going to talk about inductors. Now, what is an inductor? How would you make an inductor, a discrete inductor? How would you make it? Yeah, any suggestions? The very rudimentary inductor is a solenoid, right. Think of a core, iron core, let us say, and there is winding, copper winding around this core. Okay, that is your typical discrete inductor. You can also make this core in the shape of a toroid, etcetera, etcetera. So, let us think about this. This is a solenoid. Let us assume that the solenoid is infinitely long. Length of the solenoid is huge, okay. And let us say we have as a result packed in a lot of turns in the solenoid. Let us say there are n turns per meter in the on the solenoid. Okay, this is our assumption. Now, later on we are going to say that the solenoid is of length L, but for now let us make the assumption that this length of the solenoid is incredibly long, infinitely large. Okay. Now, what happens? How does this work as an inductor? So, first of all, when you push a current, through a wire, it creates a magnetic field. So, if I have a wire, current going through a wire, it creates a magnetic field around it. How do you know the direction of this magnetic field? By the right hand rule, right. You take your right hand, the thumb points in the direction of the current, then the curl of the fingers corresponds to the direction of the magnetic field. So, if what I have drawn on this, I point my thumb in the direction of the current, then basically the curl of my fingers is going to give me the direction of the magnetic field, okay. And the magnetic field is going to go around the wire, fine. If you make a loop of wire, loop of current, consider a loop of current, current is going round and round. What is going to happen in this case? The current on the left side is going to create a magnetic field that is going to point into the plane of paper. The current on the right side is also going to do the same thing. Okay. Now, if you draw the side view of this, then you have basically got a current looping around, and the magnetic field will look like this pattern. Okay. So, this is your typical dipole magnet. It has a north pole and a south pole. So, basically as soon as you have a loop of current, it behaves like an electromagnet, right. It has a north pole and a south pole, and magnetic fields are looping around, fine. This picture is fine. So, any loop of current basically works like a magnet. Now, if I have got so many loops of current, how many loops of current have I got in this solenoid? I have got n times L loops of current. Okay. All of these are individually magnets. All of these loops of current You can think of each of these as magnetic dipoles, right. So, as a result, when the current is what I have drawn, there is going to be magnetic field going into the core, and this magnetic field is going to loop around. Okay. So, this whole thing is now going to behave like an electromagnet. So far so good. It has flux, an electromagnet has flux, magnetic flux through the core, and Faraday's law says that whenever you try to change the magnetic flux, a voltage is induced that opposes this change. Okay. If you try to change the magnetic flux, I mean the magnet does not like a change in magnetic flux, it would like to keep the magnetic flux constant. Okay. So, whenever there is a change in magnetic flux, a voltage is developed which would be opposing the change in magnetic flux. Okay. In our case, if you have an inductor, there will be a potential drop across the inductor, right. It will generate a negative voltage, means there will be a potential drop across the inductor. Okay. This potential drop across the inductor is proportional to d phi by dt, not just proportional, it is equal to. Okay, where phi is the magnetic, the flux through the solenoid. Why would the flux want to change? The flux would change if the current changes. Okay. So, what is the relationship between the current and the flux? Well, now I am going to draw the top view, the cross section of this solenoid. So, this is my core and I have got current spinning around the core in this direction. So, when I draw the cross section of the solenoid, it basically looks like this, and the current is spinning around, and I have got n times L such loops. N times L such loops are there. So, each of these loops is going to contribute flux, right. Each of these loops is going to contribute flux, which is proportional to I. Now, what is the exact amount of flux that is going through the core of the solenoid? So, to do that, you use Ampere's law. Do you remember Ampere's law? Earlier courses, Maxwell's equations. I know you are all scared of Maxwell's equations, but his equations are the final word. So, Ampere's law is just one portion of Maxwell's equations. So, if you draw a loop like this, if you construct a loop like this, then the magnetic field along this loop, the integral of the magnetic field along this loop is mu naught by 2 pi times the current enclosed. Okay. So, if I construct a loop of length L, let us say this is L, then the integral of the magnetic field is going to be twice magnetic field times L. Because this is an infinitely large solenoid, there is going to be no component on the horizontal sides, there is only going to be magnetic field along the vertical the top and bottom edges. So, 2 b times L is going to be the integral of the magnetic field, and this is going to be equal to the amount of current that is enclosed in the loop, mu naught by 2 pi times. Okay. And of course, this means that the magnetic field inside the solenoid is mu naught times I times n divided by 4 pi. So, therefore, the flux is the magnetic field over the entire area. So, the entire area of this, let us say this has a radius of r, then the flux is going to be b times pi r squared. Did I do it correctly? Yes. So, this is my flux. Now, the voltage developed across each of these loops is the rate of change of magnetic flux. So, the total voltage developed is going to be the voltage developed across each loop is the rate of change of magnetic flux. The total voltage developed is going to be d phi by dt times n times L, that is the total number of loops that I have. Okay. Now, the inductance times d I by dt is the potential drop across the inductor. So, what is going to be the inductance over here? This quantity is the inductance. So, that is how we come up with the inductance of a solenoid. Now, first thing to understand is that there is a potential drop only when there is a change in the current, otherwise there is no potential drop. The flux through the inductor would like to be a constant. Okay. Whenever there is a change in flux, the inductor creates a voltage drop which opposes the change in current, the change in flux, I am sorry. All right. Now, on an IC, how would you make this? How would you make this solenoid on an IC? Well, one way to conceive of it is you draw your loop in metal 1 and then put VRs and then go to metal 2 and draw another loop and then put more VRs and then go to metal 3 and then do another loop and then put more VRs, go to metal 4, do another loop and then put more VRs, go to metal 5, do another loop and so on and so forth. You could do it like this. it is conceivable of doing like this. The biggest problem here are the vias. Each via is highly resistive. Each via looks like a resistor of something like 5 ohms. What is a via? Anyone who has worked with PC boards, do you know what a via is? When you make a 2-layer PC board, you drill a hole and you plate the hole, right, that is a via. We do the same thing on an IC while making ICs. So, there is metal 1, there is metal 2, in between there is oxide layer. Now, when you want to make a via, you punch a hole over here. Okay, you punch a hole, hole has to be of specific depth and specific diameter, that is the diameter of the via. You punch that hole and then you pour metal inside and you have got your via, right. It is a very narrow hole that we punch, as a result it is highly resistive. Typical resistance value is something like, it could be as high as 5 ohms. There is also a probability associated with the via. There is a probability, non-zero probability, that when you are punching the hole does not go through. So, what if you punch a hole and it does not go through? Then no contact is made, in fact you fail to make contact. So, that probability is also there. It is a non-zero probability, and because of this non-zero probability there is going to be a distinct possibility that your chip is going to fail, because you have failed to make contact. So, therefore, you put a lot of vias in parallel, right, you put hundreds of vias in parallel and hopefully some of them have made contact, which is going to establish connectivity between the 2 metal layers. All right. If you put hundreds of vias in parallel, then each via is 5 ohms, you have made 100 vias in parallel, then the total parallel resistance is going to be 0.05 ohms, 100 vias in parallel, right, 5 by 100. So, it is good practice to put a lot of vias in parallel, so that first of all some of them have to punch through, secondly you get much lesser resistance. Why is resistance important for us? Because you are trying to make an inductor. If you put a series resistance, a resistance in series with an inductor, then what is the Q of this? Okay. The larger this quantity, the lower the quality of the inductor. So, you want an inductor of high quality. When we are talking about an inductor, we want R to be 0. Unfortunately, it is not possible, but we would like R to be 0. Okay. So, this is one way that we could make an inductor. It is not usually done. This is not usually the practice because of this via problem. We do not want to put vias in the path of the inductor, because vias are resistive. We want to put metal, we want to put high conductive metal all over the place, we do not want vias. So, what is done is, you have the solenoid which is a spiral, you compress it. Okay. You have seen a spring, think of a spring and think of compressing the spring onto one plane. What are you going to get? You are going to get a spiral inductor. Okay. So, this is what we typically make on a chip. We basically treat the solenoid as a spring and flatten it onto one plane. So, we can do the whole thing with just one metal layer, and what you have got over here is a spiral inductor. Okay, it is a very crude approximation of a solenoid. Remember, the earlier design was also quite crude. I mean, no way can you call this a solenoid, but anyway, this is what we do. What is missing? The core is missing. What is the problem with that? Why is the core important? The magnetic core. No, when you make a solenoid, you put an iron core inside it. Now it is missing. We can't put iron on the chip, right? And alternatives of iron are cobalt and nickel. We can't use any of those on a chip. We only have access to copper, maybe aluminum, right. So, the core is missing. So, what? What happens when the core is missing? You see, what the core does, what iron does is it likes to capture all the field lines, the magnetic field. Magnetic field would rather travel through iron than through air. Okay. As a result, when you have your solenoid and you have an iron core inside it, the magnetic field lines would rather travel through the iron as opposed to the air. So, as a result, no magnetic field travels through air. As a result, you get the entire magnetic field traveling through the iron core. So, there is no magnetic field that leaks out through these gaps. No magnetic field leaks out. Okay. In our case, everything is air. So, as a result, there is going to be leakage. So, there is going to be individual magnetic field also around each wire. So, those field lines are actually going to leak out, they are not going to travel through the center. We would like this thing, we would like this entire structure to work like a magnet, like an electromagnet, right. We would like the magnetic field to come out and go in a circle, right. This is the plane of the inductor. We would like the magnetic field to come out through the center and go around and come back. That is how we would like it to be. Unfortunately, there is considerable amount of leakage. Each of the peripheral loops will have their own small amounts of magnetic field going around them. Okay. And as a result, there is leakage, flux leakage. Okay. So, the quality of the inductor is not that great. I mean, the equations do not precisely apply as before. Fine. So far, so good. Okay. So, basically the idea is this, that this structure is a plane, the inductor is a plane and we are trying to make an electromagnet. The magnetic field lines are going to come out and go through the substrate, come back like this. That is the idea. So, let me draw in 3D. These are the two nodes of the inductor and this is how we want the magnetic field lines to look like. Depending on the direction of the current, right, and the inductor opposes the change in this flux, the magnetic flux that goes through the core. Agreed? So, this is what we are working with. All right. What do you think are going to be the non-idealities of this? First of all, let us come up with some approximate idea of what the value of this inductance is going to be? Is the value of the inductance going to be proportional to the number of turns? Look, when we talked about a solenoid, the value of the inductance was mu naught by 4 r squared n squared L. Okay. What is L over here? You have really compressed everything. So, really L was not really the thing. We had n turns per meter and n times L total number of turns. Okay. So, if I have some total number of turns, that is what I have got here. I do not really have any length anymore. The inductor has been compressed to one plane. So, I have got a total number of turns. So, it is definitely going to be proportional to the total number of turns. Okay. Next term n also reflects the total number of turns. Does it reflect the total number of turns? Where did it come from? It came from the, we constructed a loop. We wanted to find out the magnetic flux. So, first we wanted to find out the magnetic field. We constructed a loop and used Ampere's law. We did the integral of the magnetic field along that loop, right, and found that that was proportional to the current going through that loop. So, here probably that loop is going to look like this. Okay, something like this, or let us say that loop is like this, right. So, there the total current flowing is proportional to the number of turns, not the number of turns per unit length anymore, fine, and that length part is gone now. So, the integral of this is going to be the size of the loop times the field, basically the length of the path times the field. That is going to be the integral of the loop, and then you figure out what is basically the magnetic field you have got at that radius, and then you compute for different radii magnetic field, and then you have to integrate the magnetic field, that will give you the total flux. Fine. This is how it is. So, the inductance should be proportional to the square of the number of turns, roughly speaking. What is this r square doing here? Where did this come from? This came from the flux pi r squared, we multiplied by the area, right. So, here what is this radius? The inside radius, the radius of the core. Okay. And then mu naught by 4 is just a proportionality constant. So, this is what we basically expect. We expect our inductance value to be proportional to the square of the inside radius, should be proportional to the square of the number of turns, and besides these two there should be a proportionality constant, some factor. Agreed? This is the total value of the inductance. Fantastic. If I have got your agreement on this, then let us proceed to the next step. What are the non-idealities of this inductor? You have studied power systems, Yeah, magnetic circuits long back, maybe in your first year as an undergraduate or second year as an undergraduate. So, there is a magnetic core and there is a transformer, you put a primary winding, you put a secondary winding. What are the different non-idealities? Do you remember? Anyone? Core loss and copper loss. Yeah. So, the same two things are going to apply over here. So, first let us do the copper loss, because it is easy to do it. I have got an inductor, the wire has resistance, unavoidable, the wire has resistance. Okay. What is the resistance of this wire? You basically count the number of squares that is inside this track and multiplied by the ohms per square that the foundry has given. So, the surface resistivity times the number of squares that are in this. That gives you that gives you the copper loss. So, the model for copper loss is basically something like this. You have your inductor and the copper loss, if you are pushing a current I through the inductor, then the amount of power lost in the inductor is going to be I times R squared. I am sorry, I squared times R, that is the amount of power lost in the inductor, which basically means it is also associated with a voltage drop, right. It is as if this copper loss contributes a resistor which is in series with the inductor. It is easy to intuitively see that. Okay. The next item, which is much more involved, is core loss. What is core loss? What do you think is core loss? Okay, not everyone remembers what is core loss. Now, let us go back to this 3D picture. So, first of all, how does this inductor work? I push a current through the inductor. Okay, when I have a current through the inductor, it creates a magnetic field. Magnetic field creates a flux through the inductor. When I have a changing magnetic flux, it induces an EMF or it induces a voltage to oppose the change of magnetic flux. That is how the inductor works, right. So, it does not like a change in EMF, change in flux. So, it generates an EMF which opposes the change in magnetic flux. Now, this change in magnetic flux is everywhere. Okay. It does not have to be just the change in magnetic flux through the inductor. Magnetic flux does not like to change anywhere. So, let us say this is the inductor. Okay. The inductor itself does not like a change in magnetic flux through it, but other objects also do not like change in magnetic flux through them. Okay. Say this is the inductor and this is my table over here. So, the inductor does not like change in magnetic flux, the table also does not like change in magnetic flux, and both of them are going to create EMFs that oppose any change in magnetic flux. Right? This is Faraday's law of induction. Now, let us look at the 3D picture. When I have this inductor, it is going to be over a ground plane. So, I have got a ground plane that I had not drawn in this diagram, but it exists. So, there is a ground plane underneath the inductor. What ground plane are we talking about? We are talking about the substrate, the p type substrate is hanging underneath the inductor. The IC, the base of the IC is a p type substrate. On top of it, somewhere on top of it, you are making your inductor, constructing your inductor, but the base of the IC is the p type substrate. P type substrate is conductive material, am I right? So, and also you are going to connect it to ground, presumably, may or may not connect it to ground, does not matter. There is a plane. Okay, for now this, let us not worry about the ground business. There exists a plane underneath the inductor, and this particular plane also does not like a changing magnetic flux through it. Whenever there is a changing magnetic flux, it is going to oppose it, right. So, let us draw it in a different way. Let us say this is my plane and this is my inductor. I am just going to draw one circle, okay, or think of it like a solenoid. Okay. And the field, there is some magnetic field inside and magnetic field outside. So, this is like an electromagnet, and all of these field lines go right through the inductor, hit the ground plane and then come out and again go. It is like an electromagnet, right. Okay. So, now that we have this, what do you think is going to happen when I try to change the magnetic field? When I change the current, the magnetic field is going to change. When the magnetic field changes, there is going to be a changing flux on the ground plane, on the plane beneath, there is going to be a changing flux. What is going to happen as a result of the changing flux? Whenever you have a changing flux, there is going to be an EMF, a potential that is developed as a result of the changing flux, right. So, you can kind of think of this as if so, let us say there is a loop like this on the ground plane, there is a changing flux through that loop, right, and when there is a changing flux through that loop, there is going to be an EMF developed across the boundaries of the loop, and what is going to happen as a result of that? There is going to be a current flowing around the edge of the loop. So, I am going to try to make this a little larger in size. So, this is the ground plane, and every time I have a changing flux, I have a changing magnetic sorry, I have an EMF developed in the loop on the ground plane, and when I have an EMF developed in the loop on the ground plane, what is going to happen? There is going to be a current on the ground plane. If there is a current on the ground plane because of no reason, I mean I did not want a current on the ground plane looping around like that, but now there is a current looping around like that on the ground plane. These currents are called eddy currents. So, the currents looping around in the ground plane beneath the inductor. Fine. When there is a current looping around on the ground plane, there is going to be a loss in terms of power. Okay. Think of it this way, you apply a voltage across the inductor, let us say it is a cosine varying at a frequency omega radians per second. So, you apply this changing voltage across the inductor. As a result of this, you are going to get a changing current. What is the magnitude of the current? Okay. Now, the magnetic flux is proportional to the current, right. No, I think I am going to work with the sines and cosines because I like them. Something like this. This is going to be the current flowing through the inductor. Now, there is a current flowing through the inductor which is changing at the rate V by omega L. No, there is a current V by omega L sin omega t. So, the flux is going to be proportional to the current. The flux hitting the plane beneath is also going to be proportional to that current. Now, d phi by dt is going to be proportional to V by L cos omega t, right. That is your d phi by dt. Now, if d phi by dt is proportional to V by L cos omega t, then the EMF developed is proportional to d phi by dt. EMF developed across that particular loop is proportional to V by L cos omega t. Okay. And if you have an EMF that is developed across a loop, then you are going to have a current through the loop, which is the EMF divided by the resistance of that loop. Okay. And therefore, there is going to be a power loss which is equal to EMF times the current. Fine. So, you are going to have a power loss which is proportional to the square of the voltage that you applied across the inductor. So, effectively this is going to look as if there is some sort of a resistor over here, although it is not really taking out some current, it is actually taking out some current. because of leakage, flux leakage. So, it is almost like there is a resistor which eats up some of your current and creates a loss. So, in your model for the inductor, you will have because of core losses, it will look like a resistance in parallel. Because of copper losses, it will look like a resistance in series. So, this is more or less some sort of a model for the inductor. Okay. What else? Are there any other non-idealities? Well, there is one obvious non-ideality. If we talk about a plane now beneath the inductor, then there is an inductor to plane capacitance, right. Okay. There is one more thing. Between every turn, there is a capacitance, wall to wall capacitance, right. So, all of these capacitances are really going to come inside this. So, the final model for the inductor is going to be pretty complicated, depending on how well you want to simulate your inductor or how accurately you want to model the behavior of the inductor. Your model is going to be very, very complicated. The copper loss and the core loss. Copper loss corresponds to the series resistance that you see. Core loss is going to appear as a parallel resistance. It is just a loss. It is not a physically connected. It is not the loss associated with the core loss. It is not physically connected to the system, but it is still going to eat up your power, right. And then there are going to be parasitic capacitances all over the place. So, this is my final model for the inductor. We are going to stop here. In the next class, we are going to see how we can design good inductors. And then we are going to move on to the next topic. Okay, thanks.